Hey, hello guys, welcome, welcome, and the name is Karim. Today we are going to see moving charges and magnetism. Well, first let me just give you a basic introduction about this lesson. This lesson is very heavy, really believe it or not. This is kind of heavy, not very heavy, it is kind of heavy. There are a lot of variations in this lesson, there are a lot of things that you have to get into your brain. Okay, but if you are strong in current electricity, then this lesson might be a little bit easy, but the derivations are derivations. Okay, so for this, which can help you a lot is the trigonometry. Well, you all would have studied right, trigonometry of class 10th, that's enough. Then yeah, current electricity concepts, basic concepts, that's it, that's enough. So now we are going to start with moving charges and magnetism. And magnetism. Okay, so what are the concepts that we are going to discuss? First of all, we will just see some basic things about magnetic field. In our class 10th event, we would have studied about magnetic field, right? Very basic definition. If you ask me what's the very basic definition, it's going to be the field around a magnet. Okay, well that's something that's very basic definition. The field that is around a magnet. Around a magnet. This is what the very basic definition is. Well, coming to our level definition, okay, so coming to another definition, we can say that the moving charges produce the magnetic field. Okay, a field around it, and that field is what known as magnetic field. The moving charges in a conductor produces a field. A field around it. So this field is what known as magnetic field. Then it is actually represented with beta or B. Okay. B, normally by B when we or also, okay, it's kind of mixed up. Then coming to the history lesson, again we are going to start with history. It's first the person who observed this magnetic field is Ørsted, H.C. Ørsted. What's the full form? It's Hans Christian Ørsted. Okay. So Ørsted, okay, or H.C. Ørsted, where this person is the first one who has observed it. We all know very simple thing about the compass thing, right? The compass story, where there was this circuit. Okay, he placed a conductor. Okay, he placed a conductor, and it was actually connected to a battery, so that current was flowing in there. And also when he placed a compass, the complex got deflected. See, on what basis does this complex work? All these compass. On what basis does all these compasses work? It works based on the magnetic field that is produced by the Earth. The time, okay, in his timeline even they have found that Earth is actually giving some sort of field, and that field, based on that field, they have formed this compass, and they know all these basic principles of compass. Wait, I don't know why it comes as complex. It is compass. Even if I say complex, take it as compass. Okay, so compass. And also when it was kept near to a conductor, he was able to sense that there is a deflection in the direction needle of the compass. Actually, which means that this conductor is able to produce some sort of magnetic field, and when he takes it a little bit away, again it comes back to its normal position, because the magnetic field that is produced by the conductor is actually short range. It is a very short range, and as it reduces with time, as it reduces with distance, it reduces with distance. Okay, so in order to prove this, on reversing the when a current carrying coil, I will be just reading what is the statement. When a current carrying coil is placed near to a compass needle, Oersted observed that there is a deflection in the needle. It gets deflected towards west. Okay, it gets deflected towards the west. Got deflected towards west. Then on reversing the direction of the current in the wire, the north pole of the needle gets deflected in the opposite direction. Okay, so then the north pole, see a needle, if this is what the compass is, then the needle is there, right? So in this there will be north pole and then south pole. That means that the north pole is deflected to the opposite direction. Okay, well, mostly questions, even if they ask question, then they will be asking who is the person did, then how did it get deflected, all these values they will be asking. Other than that, those many questions will not come. Okay, then after this, because there is a lot of concepts that they can ask, okay, why will they cover this one? Next is a very basic example. I think we have studied this also in our class 10th itself. What he did is, he has taken a current carrying conductor, and then he connected, he connected this current carrying conductor to wires. Okay. Two wires, and wires were connected to the battery. Okay, so then what is there is, then a cardboard was kept over there. Then, so we all know that there will be current flowing in this conductor. This is what the direction. Now the iron flakes or metal flakes that can be magnetized or that can be attracted by another magnet. Any material that can be attracted by another magnet, okay, those materials were actually put on that cardboard, and now the current has started to flow. Then what he did is he slowly tapped on that cardboard. As he was tapping, what he was able to observe is that those fillings were able to form concentric circles. It was able to form concentric circles. The same thing only was also observed with the magnet. See, if this is a magnet, if this is north pole, if this is south pole, then the south pole is actually considered as negative, this north pole is considered as positive. Okay, so all these magnetic fields are coming like this. Okay, like this they all get coming. Okay, so when those fillings were dropped, before it all got attracted, they were all in here, okay, exactly the place where I've drawn these lines, right? So those lines were the traces of those fillings, iron fillings or iron flakes. Okay, here at all, those fillings were there. So from this, they were all able to conclude that along with the electric field, another field was produced one and only when charges are in movement. Only when charges are in movement, then iron fillings or all these were able to be, okay, they were all arranged in this particular shape. And also you have to note that magnetic field is there, right? It will be in concentric circles. It will be in concentric circles. Circles. That means if this is the rod, then the magnetic field that will be produced by the rod will be like this. See, concentric circles. Like that will be going. Okay. Yeah, so this is what the very basic thing that you have to know. Then after that, okay, so in order to say the magnitude of the magnetic field or the strength of the magnetic field, in this place you can keep a galvanometer. So galvanometer is, in the structure wise I'm saying, it is kind of similar to the compass. It will be also having a needle. Normally the needle will be like this. When there is no magnetic field, it will be exactly perpendicular. Okay, it will be looking at the sky. Okay, I will be like this. Then when magnetic field starts to produce, then automatically there will be deflection by some amount of angle. Okay, there will be some amount of angle. It can be in this direction or also it can be in this direction. I've never seen a galvanometer in my life, so yeah. There will be some sort of deflection. We can say that it is by theta. Okay, theta is also directly proportional to the amount of magnetic field that is produced. Okay, theta is directly proportional to the magnetic field. Is directly proportional to the magnetic field. Then, yeah, intensity of the current is also directly proportional to the intensity of the magnetic field. Number of concentric circles is also proportional to the intensity of current. If in case the distance between two concentric circles, there will be some sort of distance between these two concentric circles, right? If that is very less, the distance between these two concentric circles is very less, then that says that the concentration itself, it's actually coming as concentration, because the previous video was chemistry that I had taken. Okay, the strength of the magnetic field will be very high. So I can say that direction of magnetic field, no, just okay, intensity of current. Intensity of I is directly proportional to intensity of magnetic field. Yeah, so that's it. This is what the basic concept is that you have to know. Okay, so coming to some laws. There are some laws that have been given by a few scientists. A lot of scientists are there. First is right hand thumb rule. This is a very simple rule. We all would have studied this, right? So where the thumb and then remaining 4 fingers. Amongst this, thumb indicates the direction of current. Okay, so these all indicates the direction of the magnetic field. Okay, so how first you have to take your right hand. So this is what the thumb, right? So first you have to take a conductor. Okay, for an example, if this is the conductor and if the current is flowing in this direction, okay, so that means you have to place this thumb in the direction of this current. Then automatically these 4 fingers has to be curved. So when you are curving them, the direction, see, it's coming like this, right? I'm kind of weak in determining whether it is clockwise or anti-clockwise. It is anti-clockwise, okay? It's anti-clockwise. Okay, so it's all revolving in this side. So that means when the current direction is this side, the magnetic field's direction will be this side. Like that you can easily say. Okay, so this is what in this right hand thumb rule. Then after this, we are having also screw rule. Okay, then also, yeah, yes, screw rule. What's there? So screw, for an example, if you are taking this as a screw and if you are taking this as the wall, so you are just going to you are rotating the screw. When you are rotating screw in this direction, this is clockwise. Okay, when you are rotating in this direction, this is clockwise, right? So it goes what? Inside. So clockwise means inward only, correct. Okay, so clockwise means inward only it is going. Also the screw goes inward only. When you are rotating like this, it comes automatically outside, right? So that means anti-clockwise na outside, clockwise na inside. Clockwise. Then anti-clockwise. So clockwise means inward. Okay, outward. Then after this, what we are having? We are having Fleming's right hand palm rule. Okay, Fleming's right hand rule or Fleming's right hand palm rule. Okay, okay. So, see, you are going to consider these fingers, okay, right hand now. So you are going to consider the right hand, where here, okay, so, no, that's not right, well, okay, see, this is what my right hand is. Yeah, it is right hand only. Where in this, what you are going to do is, this palm is there, right? In this palm, you have to write force. Well, don't write in your examination. Then you will be thrown out of your examination hall. Keep it in your brain. Okay, so the palm is the force. That is the magnetic force. Okay, magnetic field will be also producing some sort of force, like how we are having electric field. Also, then we are having force, right? The attraction force, like that. Magnetic will be producing force. Magnetic field will be producing some sort of force. Then these four fingers always indicates magnetic field. Always. Also in the right hand thumb rule, in the right hand palm rule, it indicates only the direction of the magnetic field. Then this thumb indicates the current, just like this. Okay. So I. Okay. So for an example, if the current direction is like this, then these four fingers, then the magnetic field direction is like this. Then automatically the force that is produced by the magnetic field will be like this. See, this is facing towards you only, right? So that means it is like this. So yeah. Okay, so I can say that thumb over here, fingers, then the palm. Okay, the thumb indicates the direction of the current. Okay, these four fingers indicates magnetic field, okay, direction of the magnetic field. Then the palm indicates the force of the magnetic field, the force that is produced by the magnetic field. Okay, see, imagine now we are going to see ampere swimming rule. Imagine a person swimming along a current carrying wire in the direction of the current facing a magnetic needle below the wire. Then the magnetic north pole of the needle deflects towards his left hand. Okay, so this one not required. Well, see, if a person is just swimming. Okay, imagine a person is swimming. I'm not going to write this. Okay, a person is swimming in this. Okay, current is also flowing in this direction only. There is this needle. Okay, then the north pole of the needle. Okay, so to determine which direction, okay, in which direction the needle gets deflected, the north pole of this needle will be deflected towards his left hand. North pole of the needle will be deflected towards his left hand. That's it. Okay. Then after this, yeah. So first of all, what is the purpose for this? Okay, for this, the purpose is to determine the direction of the magnetic force. Okay, the direction of the force on the current carrying conductor in a magnetic field. The direction of the force. Yeah. So the purpose is to determine the direction of the force. Okay, after putting this rangoli, now we are going to see about magnetic flux. Okay, magnetic flux, just like electric flux, magnetic flux is. Okay, so what is this magnetic flux? See, this is also represented as phi 1t. This is also represented as phi 1t, which is equal to what was it equal to in electric field? Okay, it was equal to, electric field is equal to flux per area. So flux is equal to electric field into area. Electric field into area is equal to flux. Here also, okay, here it is magnetic flux. Sorry, electric flux. So here it is magnetic flux, which can be kept as B or which can be kept as M. Okay, so B, which is equal to, instead of electric field you are going to put here magnetic field, which is B. Okay, magnetic field into area. Here this is also vector, this is also vector quantity, and here what you are doing, here you are doing dot product, here you are doing dot product, so which makes flux is equal to B dot A into cos theta. Correct. Okay, cos theta. So magnetic flux is, make sure that you are writing the cos theta, do not confuse it with sin theta, since it is dot product. For dot product we will be using cos theta, for cross product we will be using sin theta. Okay, so then what about its SI unit? What about its SI unit? Tesla, yeah, SI unit. See, which color shall we use? We will use light pink. Magnetic flux is equal to, no, electric field, sorry, magnetic field is equal to magnetic flux whole divided by area, right? So for magnetic flux, the SI unit is Weber whole divided by meter square. Okay, which can be said as Weber meter to the whole power of minus 2, like that you can write, or which is also equal to Tesla. I wish I had this car. No money. Okay, so SI unit is Tesla. Then coming to the CGS unit, it's equal to gas. Sorry, Tesla is not equal to gas. The CGS unit is equal to gas. Okay, so the relation between Tesla and gas is 1 Tesla is equal to 10 to the power of 4 gas. Kind of important. You have to memory this. Okay, so yeah, we have completed as much as possible. Okay, now what we are going to see is some basic things. See, there is also another lesson. I was thinking that I can upload a 5 hours video completely based on electricity, electrostatics, electrodynamics, every concept. I think, but I cannot stand for 5 hours. That's what my problem is, and I don't have 5 hours of time also. But it will be very helpful for me and also for you all. Okay, so coming back to here, what is there? First we are going to see about superposition of magnetic field. superposition of magnetic field. Yeah, see, it is a vector quantity, right? So what we will be doing for vector quantities? For vector quantities, B vector net is equal to B vector 1 plus B vector 2 plus B vector 3 plus x on B vector n. Okay, so this plus is actually based on the direction of the magnetic field. It is based on the direction of the magnetic field. Okay, see, if in case they both are anti-parallel, then what we have to do, we have to subtract these two. For an example, I'm just going to consider these two magnetic fields. Okay, these two magnetic fields. If in case those two magnetic fields are opposite in direction, then what we can do, we have to subtract. If they both are same direction, then we have to add. If they both are in any other angle, for an example, if they are in some other angle other than 180 or 0 degree or 360 degree, then we have to use the vector law of addition, which is A vector plus B vector is equal to root over A square vector modulus of A square plus modulus of B square plus 2 modulus of A into modulus of B into cos theta. Okay, this is what the formula of this. Okay, perfect, all of them right. Where the theta, this theta is the angle between A vector and then B vector. It can be any angle. Okay, so then after this, what we are having magnetic field is equal to some other formulas. We are going to check about magnetic field. What formula did we see till now? What is the formula that we see? We have seen that magnetic field is equal to magnetic flux into area. That is the one and only formula that we have seen. In terms of vector, we can add also cos theta. Okay, so I will write some formulas of magnetic field. First of all, that formula that we have seen there, right? So formulas. Also some derivations of formulas also we are going to see. Okay, so first of all, magnetic field is equal to flux, okay, of magnetic flux into area of cos theta. Okay, this is the first formula. Then what is the second formula? We can say that magnetic field, yeah, so magnetic field is equal to force whole divided by m. Yeah, force whole divided by small m. What is the small m? Small m is the pole strength. Okay, small m is the pole strength. You can say, yeah. Okay, so magnetic field is equal to force per small m. What is small m? M is actually pole strength, which is equal to charge of that particular. Wait, I will say. See, for an example, if this is what a magnet is, okay, or a conductor. Okay, let us keep that this is a conductor. In this charge will be there, right? Okay, let it be electron. So this electron will be going in such a speed. Okay, electron will be going in such a speed. So that charge is what Q. Okay, the charge of that particular body that is moving. Charge of the particular body that is moving. It need not be electron. It can be any charged body. Okay, that is moving, and the velocity of the body. Okay, so that is what known as pole strength. So for an example, in terms of magnet, there will be two different poles, right? North pole and south pole. In order to calculate their pole, okay, in order to calculate these two poles, we will be using this pole strength only. Yeah, and then okay, we can also write that force is equal to Newton per area. Okay, this is there. Then also we are having next point, that is magnetic strength. Magnetic strength or magnetic moment. Sorry, magnetic moment. First I'll write the formula, then over here I'll explain. Okay, so what is magnetic moment? It is capital M, which is equal to small m into length of the total magnet. For an example, if this is what the magnet is, okay, so for an example, if this is what the magnet is, and if this is what the north pole, and if this is what the south pole is, okay, so we know that this is positive, this is negative. Okay, so this one is having, and then this one will be also having about m as their pole strength. Then the total small m, okay, small m as their pole strength. Then the total strength of this total magnet is set as capital M, where capital M is the magnetic moment. Okay, like dipole moment. Okay, see what is this magnetic moment? We will just look at its concept, and also in another lesson we'll be studying. Still one more lesson is there based on electricity. When I came to 12th standard, the first day I checked the lessons, first few lessons only, and I was shocked. OMG, these many lessons are there based on electricity itself. But it's okay, not that tough. So, yeah, coming to magnetic dipole moment. Which color? Magnetic dipole moment. See, for an example, we all know, right? So if there are two different poles, okay, if there are two different charges and if they both are separated by a small distance, then we say them as dipole. So then we say them as dipole. So now it has just magnetic field inside it. But that means if two different magnetic producers or source are being separated by a very small distance, then we will say it as magnetic dipole moment. Okay, so the, wait, I will just draw one neat diagram. This is what the magnet is. This is what the north pole is. This is what the south pole is. This is what the center point is. Then this length is known as L. This length is also known as L. Okay, X. This length is X. This length is also X. So this is also, this has one pole strength. This has another pole strength, right? So we can say that this total distance, I'll take it as 2x. Okay, so this total is known as x, which is equal to 1L, we can say. Or, yeah, okay. Okay, so 2x we will keep. In some, wait, I will explain. M is equal to, what did we see over there? What did we see? That P is there now. P is equal to 2AQ. Okay, P vector is equal to 2AQ. It is a vector quantity. Yeah, it is a vector quantity. It has direction, it has magnitude, right? Okay, so is equal to 2AQ, where this 2A is the distance. And here this is what the charge is. So instead of charge, you are going to keep M, okay, M, and then distance is going to be 2x. But in some places it is given as L. Okay, that means instead of this x, you can keep it as L. Okay. Or in some places they are given, instead of this 2L, they are given it as just ML, which means that this total distance they have considered as just L. So you can write this as L. So I can write it as 2AX, which is equal to M is equal to ML. Okay, so M is equal to VQL. Okay, so yeah, this is what. Next is Biot-Savart law. Okay, very important law this is, and pretty easy law only. We will be completing this total video with Biot-Savart law. Then after Biot-Savart law, be at a point due to infinite long straight current carrying conductor. I know that infinite, that is not in our portion, but it is very important for a circular coil. Okay, in order to understand circular coil, this will be kind of helpful. Well, I can also say without this one, but this will be very helpful. You can compare these two formulas. Okay, so now we are going to Biot-Savart law. Biot-Savart law. So what is this Biot-Savart law? Here you are going to take an irregular conductor. Okay, an irregular conductor. Already I draw in a very good way. Now it's a very irregular thing. So you are going to consider an irregular conductor. It's not a regular one, it's an irregular one. I know that this is not that much important, but I'm saying, yeah, it's like me professional. Okay, stop me flexing. My English is very awful. Okay, so I'm going to keep this point as y, this point as x. Then these two are connected with a wire. The Bluetooth comes. Okay, like that, it is connected to it. Then the current, see, this is what this irregular conductor is there, right? So that means the current direction is actually like this one. The current is actually unidirectional. Okay, so when you are taking just the current direction, it will be like this. Okay. This is known as IDL, which is a vector quantity. Okay, which is a vector quantity, and this is what in this particular point, if you are taking the direction, then it will be like this. Then in this particular point, it will be like slightly like this. That in point wise, the direction of this will be changing. Okay, and yeah, this is actually ideal. Current is a scalar quantity, but when you are taking the current along with this length of this conductor, then that becomes as the vector quantity. Isn't that amazing? Thank God current is a scalar quantity. If in case it were a vector quantity, then every sum would have been a headache. So that is why every time I switch on light, I say thanks to the current, since you are a scalar quantity. Okay, so this is a point P. So this is what the point P is. We are going to see the magnetic field, okay, or the magnetic strength at this particular point due to this conductor. Okay, so how will it be? Concentric circles. Okay, concentric circles. So at this point, what it will be? I know I'm not going to destroy this beautiful diagram that I have drawn. Okay, so coming to other nomenclatures, here this point is actually with distance of r. Okay, so this is with the distance of r, and then this point is with theta degrees. Then yeah, I'm just going to consider one small segment in this total irregular conductor. If this is what the total irregular conductor is, okay, if this is what the total irregular conductor is, I'm going to consider only these 2 points. That means the length that is between this point and then this point. So only this much length I'm going to consider. So this is what DL is. So that is why I have drawn there as IDL. Okay, that is why I have drawn there as IDL. You can take also these 2 points. So you can also take these 2 points instead of those 2 points. Okay, so this is what DL is. Okay, so yeah, we have completed nomenclatures. Air sutum villa. Now, what we are going to, not villa, air sutum something. Okay, so now we are going to see the proportionalities. Some proportionalities that we are going to discuss. We have seen over here, right? Where is that? See, I have said a few things, right? Like that, we are going to discuss still some more. Okay. First is this length. If in case this length was still more bigger, then the magnetic field at this point due to this length will be also very big. If in case the length is like this, then that means the magnetic field experienced at point P will be also large. So I can see that. First I'll write it as statements. Yeah. So DL is directly proportional to the magnetic field at point P. Okay, at point P. Then after that, theta is there now. If in case this theta were big, then this magnetic field will be also big. Sin theta I can say, okay, because theta is directly proportional to sin theta. Theta is directly proportional to sin theta. So sin theta is directly proportional to beta. That means magnetic field at P. Okay, then I can say the current, yeah, the magnitude of the current also. If in case the magnitude of the current is high, then we can say that as the magnetic field will be also very high. Okay, so current is I is directly proportional to B. Then after that, it is inversely proportional to the distance. I have said in the first clip itself, I've said in the first clip itself, in this comp itself, I said that it is inversely proportional to the distance. Here also, it is inversely proportional to the distance square. Distance square. I is inversely proportional to distance square. So this law is what's it as? Inverse square law. Okay, inverse square law. In Coulomb's law we have discussed. Also in magnetic field, no, not in magnetic field. Here we are discussing, yeah, and also in gravitational. Also we have seen. Well, I haven't uploaded any video based on gravitation, but we have seen. Okay. So now what we are going to do is combine all these. I can say that magnetic field is equal to. I will give a majestic color. Okay. Not such. No, this is not majestic. Bright. Okay. So no. Okay, it's okay. So magnetic field is equal to first what is there? DL is there now. So no, DL I'll write lastly, sin theta also okay. So current, okay, I, then DL, I DL, then sin theta, then whole divided by r square. Here it should be proportional. It is proportional. Okay. In order to remove proportionality, then what we have to do? Okay, so we can write that beta is equal to, we have to put a constant. Okay, since my name starts with Kannan, it has k, I'm going to put k. Well, also in book it has given k and b, so that is why I'm putting as k. Okay, so k, I dl sin theta whole divided by r square. Okay, whole divided by r square. So now what is this k? What is this k? K is equal to mu naught whole divided by 4 pi. Okay, so mu naught whole divided by 4 pi, where mu naught is equal to, okay, mu naught is equal to 4 pi into 10 to the power of minus 7. OMG, I cannot remember. I remember all these. See, OMG, I cannot believe that I can remember all these values, because I did not read it all, just I'm directly coming and saying, and I can remember. Okay, so k is equal to mu naught by 4 pi, where mu naught is equal to 4 pi into 10 to the power of minus 7. What is mu naught? Mu naught is the permeability. What is permeability? Check before videos that I have uploaded. There it is very clear. Okay, so that means k is equal to, okay, so that means k is equal to 4 pi into 10 to the power of minus 7 whole divided by 4 pi. Okay, where 4 pi can be cancelled, so you can write that k is equal to minus 7 at air. Okay, in air it is equal to minus 7. Okay, and also it is kind of similar in other mediums. What it is going to be? Which color? This color is preferred. Okay, so it is going to be mu r. Other mediums now always r will be, which is equal to mu whole divided by, in other mediums now it will be represented as mu in between. I'll write a little bit. Good. Okay, mu r is equal to mu m in other mediums whole divided by mu naught. Naught means in air, this means in other mediums. This is relative mu naught, relative permeability. This is in other mediums. Okay, so other mediums means mu m is equal to mu r into mu naught. Okay, where mu naught is equal to 4 pi into 10 to the power of minus 7. That's it. So we have formed a very big formula itself, just by proportionalities. So just by statements. So I can say that as other mediums. This formula varies for other mediums. Okay, this formula varies for other mediums. Why am I saying the same statement again and again? Oh, something's happening. So is equal to mu naught. First, this is in air. Okay, first I'm going to write in air. Mu naught by 4 pi into r square I dl sin theta. Okay, so this is in air. Is that air or is that air or is that air? Anyways, okay, is equal to, so mu naught will be converted into mu m in medium. Okay, in medium now it will be converted into mu m. In another medium, and then it will be converted into, okay, mu naught is equal to mu m, or just mu also. Okay, so where just mu is equal to mu, okay, not, it is not equal to, okay, it will be converted as mu naught into mu r. Okay, so for this formula, so B is equal to, instead of this I am going to write it as mu naught, okay, mu naught mu r into I dl sine theta whole divided by 4 pi r square. Okay, so this, for this what I can write, instead of this total value, okay, instead of this total value I can write 10 to the power of minus 7, right? So B is equal to mu r I d l sine theta whole divided by r square into 10 to the power of minus 7. Okay, so yeah, in terms of vector, okay, in terms of vector form, vector. So what is the formula that we have? B is equal to, this is the formula that we have, right? Okay, so this is all scalar. No, but these, okay, the quantities that are over here, is scalar. That till now, if you want just the magnitude, this is okay. Just the magnitude, this is okay. But when you want in the vector form, that means along with the scalar, you have to write a unit vector. That means scalar represents magnitude. So along with this one, we have to write the direction also. Mu r, sorry, this is not in medium. I'm going to write in r only, because in medium now, all you have to do is, instead of the thing that I'm going to write, you just substitute this one. Wait, I'll say mu naught, or just k is enough, right? Okay, so just k is enough. So k I dl sine theta whole divided by r square. Okay, this formula. In case in medium, okay, in case in medium, what you have to do is, in place of k, you are going to substitute this one, this total value. This one, not r square, just substitute this one. In place of k, you have to substitute that one. Okay, in medium now, if they have asked, but vector quantity, right, in r value it will be mostly. Okay, so along with this, what I have to do is, this is actually just the magnitude. Along with this magnitude, so representing modulus, I have to put a unit vector. Okay, that is what this r square is. Which is that. So is equal to. So in place of r cap, what is this r cap? See, any vector. So for an example, r vector is equal to modulus of r into this r cap. So r cap is equal to r vector by modulus of r, which is equal to r cap. Okay, which is equal to r cap. So this one is there, right? So I'm going to substitute in place of this r cap this formula. K I dl sine theta whole divided by r square, which is r vector whole divided by modulus of r. So this modulus of r is equal to r. If you don't know, you can know now. Okay, so modulus of r is equal to r. So in place of modulus r, I'm going to write just r. So that means modulus is equal to, sorry, B vector, magnitude, magnetic field vector, K I dl sine theta whole divided by r cube. Okay, So yeah, here in this what are also r cap. R cap is a vector quantity, ideal is a vector quantity. Okay, so also in vector form we have completed. Now what we are going to see is we are going to discuss the relationship. Okay, relationship between mu naught, epsilon naught and c. What is c? C is the speed of the light. Well, this is not in this lesson at all. Okay. Okay, relationship between mu naught. Okay, so sorry, this is not mu naught, epsilon naught, and then c. Okay, so now what I'm going to do is mu naught is there and epsilon naught is there. I'm going to multiply mu naught and epsilon naught, which is equal to what is mu naught? Mu naught is 4 pi. 4 pi into 10 to the power of minus 7. 4 pi into 10 to the power of minus 7. And what is epsilon naught? Epsilon naught is equal to I can say this as 8.8541 into 10 to the power of minus 12. Okay, SI units are not required because if SI units are, I cannot remember, that's one reason, but also actually it's very easy to get SI units. I can get it, but it's not required. Okay, since it's just multiplication. Okay, so along with this, now you can do like this, and then at last you'll be getting that mu naught epsilon naught is equal to 1 by c square, like that you will be getting. Okay, but instead of doing like this, I'm going to show you how easily we can do. Well, this is what you will be getting at last. This is what the formula you will be getting. But instead of doing like this, what you can do is put here mu naught itself. Okay, mu naught multiply 4 pi whole divided by 4 pi into epsilon naught is there, which is mu naught epsilon naught. Okay, like this it is there, right? So yeah, what is this? Mu naught into, wait, what is this term? This term is k. What is this term? This term is also k, right? Okay, so don't put k square. These two k's are very different. Okay, the k that is over here, the k that we have said over here now, this k, and then the k that we have seen in the electrostatics first lesson, that k. These two are different k's. Okay, so this k is equal to 10 to the power of minus 7 into this k is equal to 1 by 9 into 10 to the power of plus 9. Correct now? Okay, step 20. Mu naught, okay, epsilon naught, where mu naught into epsilon naught is equal to, now this can go to the denominator, this total term can go to the denominator, then that will be 9 into 10 to the power of 16. Okay, so 16, which is equal to, okay, I know the handwriting of mine is very, very awful. So mu naught into epsilon naught is equal to 1 by 3 into 10 to the power of 8 to the whole square. Okay, so with this value is what known as C. This value is what known as C, and mu naught epsilon naught is equal to 1 by C square. Okay, so this is what the relation is. Mu naught epsilon naught is equal to 1 by c square. Okay, but actually this is not how formula has got derived, I think. In college level it has some big formulas. That is what I heard. Okay, but if in case I can understand, I know that I won't, but giving a try is not a mistake, right? So I'll give a try to understand. If I understand, now in the lesson that we are going to discuss this formula, I will say also the derivation. Okay, next is is B at a point due to infinite long straight current carrying conductor. That means magnetic field at a point. Okay, at a point due to infinitely long straight current carrying conductor. See, my leg starts to pain. My leg has started its perfect job, which is paining. Okay, this is what I perfectly know. I will wait. Okay, so this is what the conductor is, and coming to nomenclature. Well, this is not nomenclature. Nomenclature is to name any particular organ or any particular compound, but here it is not. Okay, so this is point B, and the distance between here and then this is both are 1. Okay, then the distance here and here is A. Okay, it is going to be A, and then the cross section that I am going to take in this total conductor is going to be this point. Okay, here I am going to take these 2 points only. So what is this point and this point? I am going to give it as A and then B. B, A, and then this total length is going to be DL. This total length. Then yeah, this is R. Okay, so this is R. This is point C. This is actually theta. This is theta. Then now we will zoom it out. Okay, zoom in. Okay, zoom it in. So what is it? It is going to be. It's going to be 0. Okay. If you are going to keep this, since it is infinitely long, this conductor is totally infinitely long, I can say that this as minus negative pi. Okay, this as positive pi. Okay, pi 1, pi 2. Negative and positive. What is this magnetic flux, right? Okay, this is there. Then what is these 2 angles? I have to give nomenclature. Okay, so here this point I can say it as what? This is going to be phi. Okay, this is going to be phi angle. This is going to be d phi angle. Okay, d phi angle. Since that angle, this upper angle is smaller than the lower angle. Oh. That's it. Okay. Now we are having a lot of triangles over there. ABC triangle. This is actually a triangle only. Because of my very neat diagram, it's now. This is one triangle. Well, this is actually, you can also say that as an arc, you can say that as a triangle, since these 2 are very small. You can consider it as per your wish. Yeah. Okay. So, now we have the formula. What formula we have? In this point, okay, in this particular point, we want. Okay, so first magnetic field is equal to K. I can write, but instead of K, I can also write full form of K. Okay, K is only since 4 pi. Everywhere in this total, in this throughout this point, this is K only. Okay, as such it is only. So K is equal to I dl sin theta whole divided by r square. So this one at this point what it is going to be, that is what we are going to see. Okay, at this point it's what is it is going to be. So here it's not theta. Okay, here it is theta only. Okay, this is what theta. Okay, so here we have kept theta, so this is what theta. I have very clearly said that the theta is what is that? Okay, so this angle is what the sine theta, the angle of this ideal and then this point. Okay, so this length. Okay, so ideal and then this one. So here also if you check it out, here this is what the length is, and then this is what the point is. So the between this point and then this ideal, see here ideal vector, this is what ideal vector is. Okay, here it is going to be straight only. Here ideal vector is going to be straight only, since it is a uniform infinitely long conductor. Okay, this is going to be straight only, and then this point, this is what the point is. So this is what going to be the theta. Okay, so sine theta, in this triangle we are going to conclude. Okay, triangle ABC. I know that we cannot do this since no space, but I will try my level best in order to complete in this one page itself. Okay, in triangle ABC. Okay, so what's there in this triangle ABC? It's going to be theta angle, right? Okay, so sine theta is equal to what? Sine theta is equal to, I'm going to draw this one. Okay, just a rough diagram. Okay, like that it is. So sine theta, where is the triangle ABC? AC by BC. Wait, this is not how it is. This is what, and this is what. See, here this is what the line is. Okay, here this is what perpendicular to this. This is what perpendicular. Okay, so this is how it is, and this is what the theta is. This is what theta is. Okay, so that means this is BAC. Okay, so sine theta. Sine theta. Okay, sine theta. This is equal to. So this is what the hypotenuse. Okay, and this is what right opposite. So AC. Okay, yeah, correct. AC. AC whole divided by hypotenuse, which is AB. Okay, so I can say that sine theta is equal to AC by AB. Now, what is AC? This is AC. Okay, so this is what AB. AB is actually DL. Okay, so AB is DL. So AB is DL. AC is equal to, now that means AC is equal to, what is AC? This point. This is what known as AC. Okay, so AC is equal to sine DL sine theta is equal to AC. Okay, now we have got this AC. Now also from this another triangle I am going to take AC. From this triangle also I am going to take AC, since these two are different triangles. Now I am going to take AC and we are going to compare those two, and at last we will be getting one value. At last you will be getting the value of R. See, this total is very big. This total formula is very big. That is why we are shortening till to this particular point. Okay, so I've got this. Now in another triangle, in triangle ACP. Okay, in triangle ACP. Okay, so in this triangle, what is phi? So this is what phi is. Okay, so this is what d phi is. Here it is actually angle. Here we are not going to take any sin theta at all. See, this one actually looks like an arc. Okay, so d phi. So this is what this arc is. Here this is what the line is, and here that is what the angle is. So what does it is? This is equal to, we have studied now in our class 10th itself, mathematics. D phi is equal to arc length. Okay, so what is arc length? Is equal to AC whole divided by, here this is actually what, this total, this length, which is going to be AP. Okay, so AC is equal to D phi into AC is equal to AP into D phi. Okay, so if I take this equation as equation 2 and if I take this equation as equation 1, then what will be happening? Since here also it's AC, here also it's AC, and also here also it is AC, like AC is equal to AP. What is AP? This is what AP, right? Instead of AP I can write it as R. Okay, so AC is equal to so AC is equal to what? AP means R and D phi. Okay, then D phi. This is what. So here, what can I write? I can write as R into D phi is equal to DL sin theta. Okay, so DL sin theta is equal to R D phi. Okay, so yeah, DL sin theta is equal to R D phi. So in this formula, what we are having in where magnetic field is equal to K into I dl sin theta whole divided by R square. So instead of this dl sin theta, I can write it as R d phi. Okay, so it's equal to K into I into R d phi whole divided by R square. Okay, so yeah, so now we have got this. Now what I can do, we can do the very good step, that is integration. Okay, do you know something? When you are deriving a formula or when you are remembering a formula, the biggest problem for me is to remember this. But when it comes to integration, it is just a unit track. That means you need not do any other thing than integration. But here you have to think. For an example, here dl sin theta is there, right? I cannot integrate it, okay? Since we have taken only the small length, okay? Only the small length is being taken. I cannot integrate it. Even if I integrate, just dl will be converted into L, that's it. More than that, there won't be any other change. But since it's an infinitely long conductor and we are having here point P, right? Well, we can directly integrate it, but that will not give us exactly this point, okay? We are just taking these 2 points, right? If I integrate it now, then it will be the total magnetic field that will be given by the total conductor at this point. But since we are very peculiar that I want only this point, so what you have to do is you have to substitute this dl, okay, this dl with any other term, okay, with any other term. So dl is there, right? So dl is over here, and there are 2 different triangles. With this one triangle even, there are 2 different triangles. So with that, you have to proceed. Okay, so here, that is why, in order to substitute this one, what you are doing, you are taking ABC as a triangle and you are taking ACP as a triangle, then you are equating them, then at last you have got this equation. From this equation, you have substituted this value, then from here you are actually, okay, now proceeding with integration. Okay, Pakka, super, done, alright. Okay. So here square is there, here R is there. I will just, okay, so here square is there, here R square is there. So if I cancel it, then it will be B is equal to, wait, before integration still some more steps are there. Okay, so I can write it as B is equal to Ki. Okay, so Ki d phi by R. So this is one formula where R, okay, so we are having R, right? R d phi, this one I have. So R, instead of R, what can I write? This is what R is, okay? So instead of R, I can write here as A cos theta, okay? A by cos theta or cos phi. How come? See, which color? This color. Okay, so this is what R now. So cos phi, okay, so cos phi is equal to A by R, cos phi, okay, A by R. So R is equal to A by cos phi. So R is equal to A by cos phi. So instead of R, I can write here as, Ki d phi whole divided by, okay, so whole divided by A by cos phi. A by cos phi. So B is equal to Ki d phi, okay, d phi cos phi by A. Okay, now integration takes place. So yeah, this you cannot integrate as already it is not a, there is nothing to be integrated over there. Well, yeah, you can take it as dB. Okay, so if you are taking a dB, then you can integrate it as integration of dB. It will be b itself. Okay, so integration of ki d phi cos phi whole divided by a. Okay, then b is equal to, here also it will be 0, here it will be b, so b 0, here it will be what, in terms of pi only you have to take. Okay, so because all these are constant, so ki by a I will take it out and it will be d phi cos phi. Okay, so it will be just b. What are the limits over there? Limits will be, see, minus phi 1, this is minus pi 2. So that is what here limit is going to be. So lower limit is minus pi 1, upper limit is minus pi 2. Okay, sorry, plus pi 2. Yes, right, plus pi 2 only is there. So I have taken this, just beta, the magnetic field is equal to ki by a. Okay, so how will this term will be integrated? This term can be integrated as sine. Okay, so sine phi. So pi 2 minus pi 1. Okay, so I can just, in this place we know that upper limit minus lower limit, already minus is there, so b is equal to ki by a into sine pi 2 minus of minus sine pi 1. Okay, minus of minus sine pi 1. So this is a term that you have got. This will be plus. Okay, so it is going to be d is equal to ki whole divided by a is going to be, so here pi 1 is equal to pi 2. Okay, here pi 1 is equal to pi 2. If you take pi 1 is equal to pi 2, then it will be 2 sine pi. Okay, if pi 1 is equal to pi 2. Okay, so if pi 1 is equal to pi 2, then it will be 2 sine pi. Then after that, magnetic field is equal to what? 2 sine pi is there. So in terms of angle, okay, see, since it is infinitely long, okay, since it is infinitely long, that means if this angle is there, right, so this rod is very infinitely long. Now what I'm going to do is I'm just going to elongate it. Okay, this rod is being elongated since it is infinitely long. It's going on, and it will be literally, it's not going to be 90 degree, but it tends to be 90 degree. Okay, because this value will be increasing, and it will be similar. Okay, similar in sense, yeah. So pi 1 is equal to pi 2 is equal to, which is similar to, okay, which is similar to 90 degrees. Similar or approximately, not similar, sorry, it's approximately equal to 90 degrees. So okay, it's 1, right? So sine 90 degree is going to be 1. So ki by a, here you are going to multiply it with 2. That's it. So here, what is ki? If you substitute k's value, which is 10 to the power of minus 7, like that also you can keep it as. So at last b is equal to 2 into 10 to the power of minus 7 I whole divided by a. This is what I've got. Then after this, what is here? The last topic, okay, of this total seminar, which is going to end with this circular, okay, magnetic field on the axis of a circular current flow. Magnetic field Okay, so magnetic field on the axis of a circular current loop. Axis of circular loop. Okay, so this is a circle. So it's a circle, and along with the circle, what is there? This is what the center point is. Okay, this is what point O is. Then, yeah. Okay, so let this be the radius, which is going to be A. Okay, so the radius is going to be A. Then, 1 second. First, you draw this straight line. Then this is B. Okay. Then after that, this is going to be point P. So this is going to be point P. Then this is going to be X. Okay, so let this be theta. Okay, so let this be theta. And one thing you have to remember, here this theta is there, right? This theta will be kind of approximately equal to 90 degrees. Here also this theta will be approximately equal to 90 degrees. Okay, so when this is approximately equal to 90 degrees, you are going to use in one point, okay, in a point of this total expression, you are going to use Pythagoras theorem, okay. So this is point B. What's happening over from here? Okay, so from here one magnetic field will be going, okay, a force will be coming, and also I'm going to consider another point in the circle itself, so let it be this point, okay, exactly opposite. Like this it can be. So if it's so since there are two different magnetic forces acting, one will be like this one. Okay, so yeah, one will be like this, and also another one will be like this. Okay, so I have got so as I said that they are going to be two different. This is going to be dB, a magnetic force. This is also going to be dB, another magnetic force. So since these are two different dBs and these two are vector quantities, what we can do? We have the formula of not resolution. Yeah, resolution also we are going to do. We are having another formula, that is parallelogram law. So according to parallelogram law, this is what head. Okay, this is what head. These was tails. So that means the resultant is going to be like this. Okay. Well, it's kind of, well, these two will be like this. I'm trying to make them symmetrical. Okay, now it's kind of symmetrical. Oh shit. Okay, so this is what going to be the resultant is. Now, also what I can do, I can also resolute that. So if I resolute this one, I'm going to take like this and like this. Okay, so here if I take this as theta and this as theta, this one, I'm going to name them as alpha alpha. So this one is also going to be alpha, and also this one is going to be alpha. So resolution now, this will be dB cos alpha. Okay, dB cos alpha. This is also going to be dB cos alpha. Then this is going to be dB sin alpha. Okay, so the resultant dB is equal to, okay, is equal to dB sin alpha. Yes, right. And also, when you are going to add them, then the resultant is going to be in this direction only, and also their resolutions are going to be in this direction only. So these two are equal. Okay. So the total magnetic field at that point is equal to dB sin alpha. Okay, so dB sin alpha. Now what I can do, where is this alpha? This is what the alpha is. So in this place, this is sin alpha, right? So sin alpha is equal to A whole divided by, this is the hypotenuse side. So hypotenuse side is going to be what? X, this is A, so this is what the hypotenuse. So hypotenuse can be named as R, no, R, no, sorry, this is what perpendicular. Okay, so this is what perpendicular. Okay, so this is what perpendicular is. So that means this is what the opposite side is going to be. Sorry, this is what the what is this? Okay, so this side is there now. This is what actually R. This total length is what R. Okay, so this is R, this is A, and also this is what the perpendicular is. So sin alpha is equal to A by R. So instead of this sin alpha, what I can write? I can write it as okay. So B0 is equal to dB A by R. Okay, dB A by R. Now what we can do, in place of dB I can substitute that formula, and also in this overall place I am going to keep mu naught by 4 pi as constant only, mu naught by 4 pi as constant. In one place I am going to substitute the mu naught value. Okay, in one place we will be substituting mu naught value, there we will be checking. Till then I will write mu naught by 4 pi as k itself. So integration of k I dl sin theta whole divided by, here this theta is this one. Okay, here theta is this one, not any other angle. Okay, I have already said that why it is taken as this one. Okay, so whole divided by r square into a by r, which is going to be r cube. So I can write as r cube ai dl sin theta a whole divided by r cube. So sin theta. So here this theta is there, right? So here I can say it as 1. Here, as I said that already, here this alpha, so here this theta is going to be 90 degree. In one place even I said, right? So that theta is going to be 90 degree, not going to be, this is kind of approximately equal to, so I can neglect it. Since this theta is very large, it will be very close to 1. So I can neglect it, and in place of there I can write A. Okay. So now I have got this. After this, integrating dl will become as L. All these are constant. K, I, R cube, A are constant, so I can take it out. dl only I am going to integrate. So when I am integrating dl, it will be just L, and length of this total circle is what? Circular loop is what? 2 pi. Okay, 2 pi r. So K I by R cube A into 2 pi r. Correct? So KIA by r cube. So KIA by r cube into 2 pi r. So in place of k, what I can write? Mu naught by 4 pi. Mu naught by 4 pi. Okay, so this and this can be cancelled, and 1 r cube and this can be cancelled. So it will be mu naught IA KIA by 2 r square. So yeah, I have got this. R square is over here. Okay. So what is R square? R square, I've got one small mistake. R is actually A. Okay, R is going to be A, so it's A square. So here it is R cube only, because here radius is not R. Here radius is A. This is what my radius, so radius is A. If in case, okay, in the beginning even if I have taken that as R, that's okay. But since I have taken this as A, I have to put there A only. So here A, like this it is. So what is R cube? R cube. R square, from here, Pythagoras theorem. Okay, according to Pythagoras theorem, I can write that R square is equal to. Okay, so R square is equal to A square plus X square. Okay, then just R is equal to A square plus X square the whole 1 by 2. Okay, so when you are multiplying these two equations, then what it will be? When you are multiplying these two equations, it will be R cube. So R cube is equal to A square plus X square into 1 plus 1 by 2, which is going to be 1.5. Instead of writing 1.5, 3 by 2. Okay, 3 by 2. Here in place of this, I can write it as B is equal to mu naught IA square by 2 into A square plus X square to the whole power of 3 by 2. Okay, I've got this equation. Now for n number of loops, that means for many loops, what you have to do is you have to multiply this total equation with n. Okay, so wait, for n number of loops, for n number of loops, what you have to do, you have to multiply this total equation. Mu naught IA square whole divided by 2 into A square plus X square into 3 by 2 into n, where this n represents n number of loops, many loops. Okay, so yeah, at center, okay, at center what will be happening? That means here it is actually a point P. This is actually point P, which is actually away from center. That means exactly at center. So at center now, this x value will be 0, right? So this is also another case. At center, what will be happening? That means x will be completely 0. So that means A square only will be there. So here the square is there, and also here this square is there. It will be both cancelled. Then it will be A cube and the square is there. So it will be just A, and in the numerator there won't be any A at all. So B is equal to mu naught I whole divided by 2A. Okay, whole divided by 2A. And for n number of loops, if in case it has n number of loops, you can multiply n. Okay. So that's it for today's video. We are going to meet in another amazing video. Till then, bye bye.